So the next part of this unit is graphing polynomial functions. And we are going to categorize our polynomial functions, and you have space off to the side, as either odd functions. Those are ones where the biggest exponent is odd. So if you had an x cubed graph, an x to the 5 graph, those we call odd functions. And I want you to write a little note. With odd functions, end behavior acts like a line. Now, when we talk about end behavior, we're talking about where does the graph end, on the negative section or the positive section. Like, you know how a line, if it has a positive slope, goes up from left to right? And it would start down here and end up here. And parabolas either open up or open down. So odd functions are going to act like lines, and even functions, those are your x squared, x to the 4, x to the 6 ones. We're going to say that the end behavior acts like a parabola. So we're going to go back to the examples that we just did to see what I mean by this. So these ones that we were just matching. The x cubed graph is an odd function because it has the biggest power being odd. And it has a positive leading coefficient, +1 out in front. If you think about a line with a positive slope, a line with a positive slope goes like this. Its end behavior, when we talk about end behavior, is really where are the arrowheads. Can you see that on the x cubed graph, it starts down here, has a little bit more fun in between than a line, and it ends up there. Okay? Same thing, the other odd one was the x to the 5th graph, but this is negative. It's still an odd function because it has an x to the 5. But if you had a line with a negative slope, your end behavior would look like this. Can you see on this one? That it started up on the left, ended down on the right. Just like imagining a line with a negative slope would do. So when I talk about the end behavior acts like a line, it tells you where it's starting and where it's ending. But yeah, x to the 5th has a lot of fun in between compared to a line. A lot more stuff going on. Then we get to our two even functions here. Both of these ones are even. This one has a positive number in front, and this one has a negative number in front. What does a positive parabola look like? It opens up with its end behavior up in the top. That matches up with this one. This one has a negative coefficient. It looks like a parabola that opens down, and sure enough, both the arrows are down on that x to the 4. And it has like the basic idea of a parabola with some more bumps and bends in the way. So this is our starting point for learning how to graph different polynomial functions. We have to recognize if things are odd or even. And in the chart at the bottom, then obviously we know how to graph lines. Positive slope, with the arrowheads on, goes like this. Negative slope goes like that. We know how to graph parabolas. If the a value is positive, it opens up. If the a value is negative, it opens down. But after that, when we get to the new ones, x cubed, x to the 4, x to the 5, line with a positive slope. If the leading coefficient is negative, I think of a line with a negative slope. And sure enough, if we add the arrowheads on here, can you see that that has that shape of a positive line? And the arrowheads on here, joining them up, would have the shape of a negative line. With an x4, positive will act like a parabola, negative will act like a negative parabola. And if we look at where the arrowheads are, they match up. And they match up down there. So now we at least know where any graph will start and finish, whether it's cubed, or fourth, or fifth, or sixth, or seventh, or eighth, or ninth. This works for any polynomial function all the way through. And this idea of acting like a parabola or acting like a line, for me, I found is the easiest way for students to remember what the end behavior. The textbook has come up with, excuse me, I think they have the x to the 5 one yet. X to the 5 is odd, it's going to act like a line, but line with a positive slope, line with a negative slope. Notice where our arrowheads are, right? That would be a positive slope. That would be a negative slope. So, this happens all the way through. And as I was saying, I think that the easiest way to remember this is to think about lines and parabolas. So if it's odd degree, right, this is where we said it acts like a line. So positive, I would draw a line with a positive slope. Negative, I would draw a line with a negative slope. I think that that visual is way easier to remember than this. As x goes to negative infinity, the graph falls to the left, and as x goes to infinity, the graph rises to the right. What they're saying is if your x's are going to the left, to negative infinity, your graph is going down. And if your x's are going to the right, to positive infinity, your graph is going up. But you could describe all of this with one little picture. And that picture is much easier to remember. Same thing here. As x goes to negative infinity, the graph is going up. As x goes to positive infinity, the graph is going down. But the picture is so much easier to remember. Same thing with the even ones. I just think of a parabola. Here it's positive. I know that it ends going upwards, negative, downwards. Much easier than the definition that they've described. Couple more definitions. Take out your highlighter. We have something called a local maximum and a local minimum. These become really important on graphs. Okay? What it means for something to be a local maximum or a local minimum is if you look around it, that point is called a local maximum there because all around it, everything's small, right? We have somebody in this class that's the tallest. They are the local maximum for this class. Guaranteed, they are not the tallest person in the world, right? The tallest person in the world we would call an absolute maximum. But there's somebody in here that is the local maximum, the tallest in this class, right? There is someone here who's a local minimum, the shortest in this class. So we can do those kind of things, right? Here we have, in that city, in that town, that person is the local minimum, okay? This one is considered a local maximum, but if you think about the whole graph, if this went down forever, this one would also be called an absolute maximum. They're not the tallest in their city, but they're the tallest everywhere. Those points are key things in calculus. So some of you are planning on taking AP Calculus next year. Some of you might be taking Advanced Math Calculus next semester. Calculus is worried about finding those points. Our algebra in grade 12 pre-calculus can't find them very well. The best thing you could do is type the equation into Desmos or into your graphing calculator and click on the point to find it. But you can't find it algebraically yet. But what we're going to be able to find in this unit is we're going to be able to find the end behavior. We know how to factor. That's what we did in 1.1 and 1.2. So if we factor, we can find all the x-intercepts. It's not hard to find a y-intercept because you can just plug in x equals 0. And then if you know those points and the end behavior, so for example, if I knew a dot here, a dot here, a dot there, a dot there, and a dot there, and I knew that it ended down here and ended down here, then I could draw the graph close to what it is in reality. What's going to be not accurate when we're drawing is we won't know how high to put these. Notice I went through the same points, but they're saying it went much higher than. I won't know exactly how high to go. Okay, that we have to wait for calculus. But this is what we're getting ready to do, to be able to graph these points. So what we're going to do is we're going to sketch things using the end behavior and using some points that we have. So we'll go to example 1. And in example 1, the first thing they would want you to do in A is, do we know what the end behavior looks like? Yes. The end behavior is going to act like a line and start down there and end up there. So if I was going to sketch a graph, what I could do with and this is always true of any graph, if you want to sketch a graph, you could just find a bunch of points. Right? I could plug in 0 for x, and I would get 0 for y. So I know this is one of my points. I could plug in 1 for x, 1 minus 3, I'd get -2. -2 for y. And I could keep doing that. I could plug in -1, which would be -1 minus 3, -4. I could plug in 3 and get 27 minus 27 and get 0. So we can plug a couple of points in, and then from there sort of go, okay, I know that it has to start down here and end up here. What do I think it looks like if it was going through those 4 points? I don't know, maybe could be something like this. How accurate do I feel right now? Not super certain. I only had 4 points. And I knew that it had to end there and begin there. It had to go through those points. But we're not super certain yet. But this is not bad. This could be the graph. I don't know if it goes much lower than this. I could check by finding more points. But for now, this is all that we're expected to do. Get an idea of how the end behavior is and draw some points. Can you see that this next one end behavior would look like this. So we could plug in some points until we felt comfortable enough to draw everything through that as well. So I'm not going to do B, I'm going to just give you your questions because I'd rather you try some. So find some table of values, think about the end behavior, and try questions 5, 6, and 8.